Hey everyone, and welcome. Today we are diving deep into the world of thermal physics. Now, that might sound complicated, but really, it's all about the invisible energy that flows all around us all the time. It's the energy that shapes our world, from a simple block of ice to the weather across the entire planet. So let's get into it. So, what is this energy really? I mean, how does it actually move from a roaring fire to a cold piece of metal? And what happens when you add it to things? How does it take solid ice, turn it into liquid water, and then into steam? Well, that is exactly what we're going to figure out today. Okay, first things first. To really get our heads around this, we have to clear up two of the most important ideas in this whole field: heat and temperature. A lot of people use them interchangeably, but trust me, they are not the same thing at all. Here's the main difference, and it's a big one. Temperature is a measurement. It's a number on a thermometer that tells you how fast the molecules inside something are jiggling around. That's their kinetic energy. Heat, on the other hand, isn't a measurement. It's the actual energy that moves from a hotter thing to a colder thing. So you can think of it like this. Temperature is the reading, but heat is the flow. Now this is probably the single most important rule in all of thermal physics. You got to remember this one. Heat always flows from a place with a higher temperature to a place with a lower temperature. Every single time, it never ever goes the other way by itself. This one simple principle is the key to understanding, well, pretty much everything else we're about to cover. All right, so we know heat is energy, and we know it flows from hot to cold. So what's one of the first things it does when it gets into most materials? Well, it makes them expand. It makes them get bigger. Let's look at a really classic, powerful example of this in action. Check this out. When a blacksmith heats up an iron ring, that heat energy gets the iron atoms vibrating like crazy. As they jiggle around, they start pushing their neighbors further and further apart, and the whole ring, it just gets a little bit bigger. This is called linear expansion. It expands just enough to slide right over that wooden wheel, and then, as it cools down, it shrinks back, creating an incredibly tight grip. Pretty clever, right? And this is a perfect example of a real-world physics problem. A blacksmith can't just guess how hot to make the ring. It's got to expand by a very specific amount to fit perfectly. So the question is, exactly how hot does that ring need to get? So how do we figure that out? Well, let's break it down. It's basically a simple three-step recipe. First, we pick the right tool for the job, which is the formula for linear expansion. Second, we just plug in the numbers we already have. The ring's starting size, the size it needs to be, and a special number for iron called its coefficient of expansion. And third, you just do a little algebra to solve for that final temperature. And boom, the math tells us the answer, 218 degrees Celsius. Okay, so heating things up makes them expand. But what happens if you just keep adding heat? I mean, things don't just expand forever. Eventually, you pump in so much energy that they do something even more dramatic. They change their state completely. Let's trace the journey on this graph. As you add heat to ice, its temperature climbs up. But then, when it hits 0 degrees Celsius, something really weird happens. See that flat line? The temperature totally stops rising, even though we're still pumping in heat. All that energy is now being used for a different job, breaking apart the bonds holding the ice crystals together. This hidden energy is called latent heat. Once all the ice is melted into water, the temperature starts rising again until it hits another plateau at 100 degrees, where the same thing happens for boiling. And that brings us to our next big challenge. How much total energy would it take to turn a 3-kilogram block of ice, starting way down at minus 12 degrees Celsius, all the way into steam at 100 degrees? This calculation is a whole journey, and it's got 4 main parts. First, we calculate the energy needed just to warm the ice up to its melting point, 0 degrees. Second, we use the latent heat formula to figure out how much energy it takes to actually melt it. Third, we calculate the energy needed to heat all that liquid water from 0 all the way to 100. And finally, fourth, we use the latent heat formula again to find the huge amount of energy needed to turn that water into steam. You add all 4 of those numbers up, and that gives you the grand total. So we know heat can make things bigger and even change them from solid to liquid to gas. But how does that energy actually move? How does it get from the stove to the pot of water? Or for that matter, from the sun to the earth? Well, it turns out there are 3 main ways that heat gets from A to B. First up, we have conduction. This is just heat transfer through direct touch. Imagine you stick one end of a metal rod in a fire. The atoms at that end start vibrating like crazy. Then they bump into their neighbors, who start vibrating, and they bump into their neighbors. It's like a chain reaction passing energy down the line. It's exactly why the handle of a metal spoon left in hot soup gets so hot. Next up is convection, and this is the one that happens in fluids, so liquids and gases. When you heat up a fluid, it expands, which makes it less dense, so it rises. Then the cooler, denser fluid sinks down to take its place, which then gets heated and rises, and you get this circular flow called a convection current. This is what's happening in a pot of boiling water, and it's also what drives huge weather patterns like the sea breeze you see right here. And the third way is radiation. This is heat transfer by electromagnetic waves, like infrared light. Now, the super cool thing about radiation is that, unlike the other two, it doesn't need any stuff to travel through. It can travel through the total vacuum of space. This is how we feel the warmth of the sun, even though it's 93 million miles away from us. It's just pure energy flying through space. All right, let's bring all these ideas home. We're going to take everything we've talked about, heat, temperature, and how it travels, and use it to understand something we've all experienced: a cup of coffee cooling down. Have you ever noticed how a really hot cup of coffee seems to cool off super fast at the beginning, but then it takes forever to finally get down to room temperature? Well, that's not your imagination. That's Newton's law of cooling. It says that the speed of cooling depends on the temperature difference between the object and its surroundings. So when the coffee's piping hot, the difference is huge and it loses heat really fast. But as it gets closer to room temperature, that difference gets smaller and the cooling slows way, way down. And that brings us to a final thought for you to chew on. Think about a thermos. Its whole job is to stop heat transfer, right? To keep hot things hot and cold things cold. So, based on how it's built, with that vacuum layer, the shiny silver surfaces, the tight lid, which of the three forms of heat transfer do you think it's designed to stop? Conduction, convection, radiation? Give it some thought. Thanks for joining me today.